When it comes to the adaptations that occur within skeletal muscle as a result of anaerobic training, both structure and function are impacted in significant ways. Over time, consistent training leads to increases in muscle size, shifts in muscle fiber types, and improvements in the biochemical and ultrastructural components of the muscle, including changes in enzyme activity and muscle architecture. These changes translate into enhanced performance characteristics like increased strength, power, and muscular endurance, which are all essential for athletic success. The muscle hypertrophy refers to the increase in muscle fiber cross-sectional area that results from consistent training. The growth in muscle size is closely related to increases in muscular strength. On a biological level, hypertrophy involves a net increase in the synthesis of contractile proteins like actin and myosin within the muscle fibers. As these proteins accumulate, the number of myofibrils, the basic rod-like unit of a muscle cell, within the muscle fiber increases. These new myofilaments are added to the periphery of the myofibrils, causing the muscle fibers themselves to grow in diameter. Collectively, this results in the enlargement of entire muscles or muscle groups. The process of hypertrophy is primarily stimulated by mechanical loading, such as during resistance training. This mechanical stress activates a number of intracellular pathways that regulate gene expression, ultimately promoting protein synthesis. Specifically, the mammalian target of rapamycin, mTOR, pathway, as well as the adenosine monophosphate activated protein kinase, AMPK, and mitogen activated protein kinase, MAPK, pathways are crucial in the regulation of hypertrophy. Of these, the mTOR pathway is particularly important for increasing muscle protein synthesis following resistance exercise. When the muscle fibers contract under load, mTOR signaling is elevated, which plays a critical role in myogenesis, the process of muscle fiber growth. Additionally, resistance training helps downregulate inhibitory growth factors such as myostatin, further promoting growth pathways. After an intense resistance training session, muscle protein synthesis remains elevated for up to 48 hours. The extent of this increase in protein synthesis is influenced by several factors, including nutrient intake, especially carbohydrate and protein, amino acid availability, the level of mechanical stress experienced during the workout, muscle cell hydration, and the anabolic hormonal response triggered by the exercise. The hypertrophy process can also be affected by exercise-induced muscle damage, which occurs when the muscle fibers are disrupted during high-intensity anaerobic exercise like resistance training. This damage triggers gene expression changes aimed at strengthening the muscle fibers to protect them from future damage. Over time, this remodeling process, combined with the body's inflammatory and metabolic responses, leads to long-term muscle growth. Although changes in muscle protein types begin after just a few training sessions, significant muscle fiber hypertrophy typically takes longer to develop. It usually requires more than 16 workouts for the cross-sectional area of muscle fibers to increase substantially. The largest gains in muscle size tend to occur early in a training program, and as training continues, the rate of hypertrophy tends to slow down. The amount of hypertrophy that occurs is largely dependent on the specific training stimulus and how the training program is structured. To maximize muscle growth, it is important to combine both mechanical and metabolic stimuli effectively. Mechanical stimuli such as lifting heavy loads using eccentric muscle actions and training with low to moderate volumes are particularly important in strength training. These mechanical factors help recruit more muscle fibers and stimulate muscle growth by increasing the size of the muscle fibers. Metabolic factors such as training with low to moderate intensities, high volumes, and short rest intervals, as seen in bodybuilding style programs, also play an important role in muscle growth. This type of training stresses the glycolytic energy system and increases the presence of metabolites like lactate, which are thought to be involved in stimulating hypertrophy. These training programs are also known to trigger a robust anabolic hormonal response, further promoting muscle growth. One of the more debated topics in exercise science is the role of hyperplasia in muscle growth. Hyperplasia refers to an increase in the number of muscle fibers, which occurs via longitudinal splitting of existing fibers. While hyperplasia has been demonstrated in animal models, its occurrence in humans remains controversial. Some studies suggest that hyperplasia may contribute to increased muscle fiber numbers in resistance-trained athletes compared to untrained individuals. But it is difficult to separate genetic factors from training-induced hyperplasia in humans. Although some data support the possibility of hyperplasia, it appears to be a minor contributor to muscle growth, accounting for less than 10% of the increase in muscle size if it occurs at all. The magnitude of hypertrophy varies between different muscle fiber types. Muscle fibers associated with high threshold motor units, typically type 2 fast twitch fibers, show the greatest potential for hypertrophy. According to the size principle, type 2 fibers are recruited during heavy resistance training, and this recruitment triggers the signaling processes that promote protein synthesis, while both type 1 demand towards slow twitch and type 2 fibers can grow in response to anaerobic training. Type 2 fibers tend to increase in size more dramatically than type 1 fibers. Anaerobic training, such as resistance exercise, can also induce shifts in muscle fiber types. Muscle fibers exist along a continuum from highly oxidative type 1 fibers to less oxidative type 2 fibers. Young with consistent resistance training, particularly when high threshold motor units are activated, type 2X fibers, which are the least oxidative, transition to more oxidative type 2A fibers. This shift represents a change in the muscle's myosin heavy chain isoform content. For example, studies have shown that as little as 2 weeks of high intensity resistance training can significantly reduce the proportion of type 2X fibers while increasing the proportion of type 2A fibers. Resistance training can also lead to changes in muscle structure, such as an increase in pennation angle, the angle at which muscle fibers attach to the tendon. Larger pennation angles allow for greater protein deposition within the muscle, which facilitates hypertrophy. Additionally, resistance training can increase muscle fascicle length, which is positively associated with force production and the transmission of force from the muscle to the tendons and bones. Other important adaptations to resistance training include increases in myofibrillar volume, cytoplasmic density, and the density of the sarcoplasmic reticulum and T-tubules. These changes facilitate hypertrophy and contribute to improvements in muscle strength. Additionally, resistance training has been shown to reduce mitochondrial density in muscles. While the number of mitochondria remains constant or may even increase slightly, the relative density decreases due to the expansion of muscle fiber size. Anaerobic training also improves the muscle's buffering capacity, allowing the muscle to better tolerate the accumulation of hydrogen ions, H+, and other metabolic byproducts that cause fatigue. As a result, athletes can experience improved muscular endurance and delayed fatigue during high-intensity efforts. Anaerobic training leads to increased storage of high-energy compounds like ATP and creatine phosphate. This supercompensation effect allows muscles to store more energy, which can be rapidly accessed during high-intensity efforts. Resistance training also enhances glycogen storage within muscles, increasing the muscle's ability to perform prolonged, intense activity. In conclusion, anaerobic training brings about significant adaptations in skeletal muscle, including increased muscle size, shifts in fiber type, and improvements in muscle architecture. These adaptations are essential for athletes looking to improve their strength, power, and endurance. Through careful manipulation of training variables such as intensity, volume, and rest periods, athletes can optimize their muscular adaptations and maximize performance.